think it's Marie. There we go, automating summarization of prep requirements. So over to you.
Thanks. Thanks everyone for taking the time out of your very busy days, I'm sure, to listen to me. So yeah, I'm Marie. I'm from the Computer Science Department, and this project was a collaborative effort between us, the University of Manchester, as well as Christian Kinderman from Stanford University in the States. And Baudelaire did all the work, right? But unfortunately he's not here. So Baudelaire was an intern that we had for about 8 weeks during the course of this project to basically do the hard work. So sorry if I don't present his work very well. He certainly probably would have done a better job. So I'm sure a lot of you who are from computer science at least are familiar with this sort of software development V-model. Beginning with requirements, you do some architecture design or analysis, and eventually you code, and then you go back up the other side and you verify and validate and make sure everything is okay. That's quite a classical thing in software engineering. There's nothing fancy there. This project focuses on the requirements engineering process, which is the very top left corner here, and tools that we use to do that. So requirements engineering, as you can imagine, has a lot of inputs. So often if you're developing a critical system especially, you must follow a sort of requirements-driven approach to development. And for the requirements for those things, for example in aerospace, you will have standards, you will have regulations, you will have system descriptions, domain descriptions, as well as whatever your stakeholder needs are. And all of those things are input into this sort of requirements engineering process, and eventually everyone agrees what the requirements are, and from those we develop specifications and code, and eventually the final system. So if something is complicated as a rover, for example, I think this is Percy, isn't it? Perseverance rover. It has lots of different components to it, but often what happens with us software engineers is someone comes and says, can you rubber stamp this and tell me, yes, it works. Think of it like a CE mark on your laptop or something. But the question that we always ask is, okay, that's great, you have a lovely robot to do something, but what should I verify? And those things usually are the requirements. But a lot of the time the requirements are ambiguous, they're not clear, and sometimes they're incomplete as well. And most often they're written in natural language. So an example here would be for a requirement, after collecting a sample, the rover should place the sample into a container. Okay, that seems simple, right? But that's not something that's very easy to programmatically verify. So it's intuitive. Certainly we all understand what that means. We can visualize what that means. But it is ambiguous. We don't know what the container is. We haven't described how we place it in. We also haven't actually said how it collects the sample. Is that a drill? Is it a laser? Is it something else? Honestly, we just don't know. So what we like, us software verification people, we like formulas that look a little bit more like this. Okay, but they're not intuitive. They're not easy for an engineer to produce, and they're certainly not easy for anyone to read. But they are unambiguous. When you get down to the nitty-gritty detail, you say exactly what you mean, and they are amenable to formal analysis. So they're easily verified, more straightforward to verify than the natural language. So NASA kindly developed a tool called FRET. It's the formal requirement elicitation tool that exists to bridge this gap. So an interface here, for example, is a requirement. It can have an ID. It's assigned to some project. This is a requirement for an aircraft engine controller that we were working on a different project with Collins Aerospace. And I think it says, if sensor faults and tracking pilot commands, the control system should satisfy some control objectives. So you can see there's still a bit of ambiguity there. We can see where it is, right? You should have seen the natural language of this, and I'm annoyed now I didn't put it on a slide, but it was like this much text. And you can see here, Fred also gives this useful diagrammatic semantics that lets you kind of reason about what the requirement means. This is the beginning of time, this is when the trigger condition is true, and that's when it should hold. And this gives us out those properties. I don't think I have it on this slide, but it gives us properties that look like this. So it takes a structured natural language and it turns it into something that's friendly for us verification people. So the motivation for this work actually came from this project that we were doing with the aircraft engine controller. So I'm not expecting to be able to read any of this. But the point of this slide is to show you that you can see there's quite a lot of repetition. So for example, this use case 5 requirement 1.1, and 2.1, they have like very similar structure here. They have a whole lot of things about sensors, a whole lot of stuff about these diff, ref, obs, and they have basically exactly the same conditions. And those were things like tracking pilot commands. I think most of that first part is just what actually meant to be tracking pilot commands when we spoke to the industry partner. But this repetition throughout the requirement set is quite difficult from a maintenance perspective. So if suddenly the definition of sensor faults or tracking pilot commands changes, we have to go manually requirement by requirement and update this really ugly equation here. And hope that we don't put an inequality pointing in the wrong direction. As you can see the problem, right? So in this specific set of requirements, we found that we had 132 redefinitions or 132 pieces of requirements that were repeated. And we built this map of what they looked like, just to illustrate exactly what they were. So we only had 9 or 10 fragments, but they were repeated quite a lot. That was before we did some refactoring, and after we did refactoring, we only had 9 of them. So we refactored these requirements. I didn't really get into this. I'll show you on the next slide. We refactored these requirements in the way that you would normally refactor software. So things like, taking a chunk of code that's repeated over and over again, putting it into a different method, and then calling the method instead. It's basic, good design, right? But it hasn't been done for requirements before. So we extended fret, it's called mu fret, our extension, and it allows you to do things like extract this sensor value thing, replace it with some identifier that says what it is, and then I only need to change it in one place rather than 132 places in the other. So we had done that work previously, but our question when we started this project was, can we automatically identify these fragments? These repeated parts. So before this, we were doing this manually. We were saying, okay, that's repeated, let's pull it out, or let's do something. But can we actually identify them automatically? Because some of these requirement sets are really enormous. This one wasn't that big, but some of them are not pretty. So we started looking at macroplication, which is a technique from the ontology domain, and it breaks up formulas into lots of subterms, and then you can find out which ones are repeated and essentially form those into macros, and then you call the macros in the way that we were calling the requirements. So what Bajidar did in this project is he developed a prototype for doing this, and he started with some serialization. So all the formulas he takes the formulas directly from Fret, and he does this serialization of them so that they can be used by his tool. He extracts all of the subterms and provides a visualization of them in this graph. This is like the least pretty part of the graph, I promise. And he does some ranking and filtering. So we also did some analysis of, well, if I refactored this fragment, for example, how much will that shrink my overall formula size by? So it wasn't just on, take it out and see what happens. It was, what's the benefit of actually refactoring that piece? And his output is like this, basically. So it gives you the formula or the subterm, how many times it happens, what size is it, and this notion of shrinking power, how many things can be improved if I do this refactoring. And he did this on a lot of requirements, because we had a lot of requirements from other studies. So we had an autonomous grasping use case for debris removal in space. We had a ventilator system. There's a mechanical lung ventilator. There's only one robot there, but we had actually a lot of robot examples that we gave him. And we had the aircraft engine controller as well. And for example, for the mechanical lung ventilator, he outputs these formulas, which are the subterms that are produced by Fret, and provides the statistics. Now there is still a bit of work more to do on this, because some of these things are sort of inbuilt to the way Fret generates the formulas. For example, if you have a triggering condition in the requirement, it always produces the formula of a kind of certain shape. So we need to do some more work on figuring out how do we remove those pieces, because we don't really care about them. They're just, the nature of how that tool works. They're not actually fragments that need refactoring. So yeah, next steps, we have to write a paper, apply for grants, incorporate the prototype into the main branch. So we're hoping to apply for an ECAS or NSF grant for this, whenever I get time to do it. In collaboration with Chris from Stanford. And I think that's all.
Thank you, Marie. Any questions?
First question is MU. What does MU stand for?
So the refactoring originally was part of a project I was working on when I was at a different university called Maynooth University. So it's MU.
Okay.
Yeah. So it's MU's fork of bread, basically. But you could call it Manchester University. It works, right?
Yeah, Mustafa.
So, how easy or straightforward or difficult would it be to integrate these two into the?
Into Fred.
Yes.
We've been talking with the development team about doing it. They're interested in doing it. To get anything integrated to any of NASA's main branch tools is not an easy task. There's a lot of paperwork involved. That's why we're hoping to start with our own version or our own fork of it that we have control over. So we have a PhD student working on that at the moment in Ireland on a funded differently. Yeah.
But they're interested.
Yeah. No, they saw great benefits in it. They have obviously we've done work on other requirement sets, but they have a lot more than we do. So they think that they're reaching a point in their own tool where they're realizing that managing these things is not trivial, and anything like this could make a huge difference there.
You talk about NASA. I think what is in my mind is I think the methodology of what called model-based system engineering methodology. I just wonder if this is kind of a digital version of module-based system engineering.
Yeah, well, it kind of fits into the same mindset. But in either case, you'd have to start with requirements, and that's
Yes, in the traditional model-based system engineering, the first step is to generate a business case in which stakeholders work together to decide what requirements they want. But of course, the original stage without digital technology, then it's harder to really pin down. I just wonder if AI has helped this process of redefining or refining or redefining.
Yeah, so we did look into that actually on a different project. So we were actually wondering if you could use an LLM to write the requirements in Fred. So if you gave it the documentation or the standards, could you produce some useful sets of requirements? And the initial results were a bit mixed. Sometimes you could produce things that were useful, but yeah, it's certainly it's kind of an open area at this point. I'm not convinced that using AI for everything is the way that we should be going, but I do think for this sort of thing, for going through documents quickly and suggesting requirements, I think it could be very useful. At this point in this work, we're assuming we already have a set of requirements. Does that answer your question?
Well, we can discuss it later on.
Okay.
Yeah, one for the coffee break. Any other questions? That's what Maria. At one point you mentioned in passing the difference that the incorrect symbol can have in some of the text that's produced on the back of this. Do you have any examples of kind of real world consequences of that kind of inputting of symbols?
Well, I mean, I put in inequality the wrong way when we were doing the aircraft engine controller thing, and in the Simulink model, the whole thing failed almost instantly.
Yeah.
So that would have been frightening if it was actually put onto an aircraft, right?
I was thinking,
And that was a very simple. That was a typo. I made a typo.
Right. Okay.
So yeah, I mean, there's lots of examples of software systems failing. Like they had that many years ago, the Ariane 5 that was converting from floating point to non-floating point numbers, and the whole thing exploded a few seconds after launch.
Yeah.
There's been quite a few examples of this. There was also a cancer treatment machine a few years ago that again had been programmed assuming the user was going to input things in a certain unit, and they were actually inputting in a different unit, and it overdosed many patients. But the requirements are wrong, basically, for that.
Wow. And the reason I mention that is when you put up a picture of the Boeing,
Yeah.
obviously in recent years Boeing has had
there's
several issues with the
wrong,
where things have gone wrong quite drastically because of sensors overriding certain responses on the
but with the MAX 8s, it wasn't just the sensors. They had kind of implemented a system that was accommodating for something else, and they hadn't told the pilots about it, and then there was a failure. So that's what caused it. So they had a system that was pushing the nose of the plane down because the plane was off balance because they'd moved the engines around. And so it was always default push the plane down. And then when there was a sensor error, that meant it wasn't, it thought it was here when it was actually here, and then it was telling the plane to push itself down again.
Yeah.
It ended up going down here. I don't know, like, that was a software problem, it was also a people problem, they had issues with the FAA at the time as well. But these sorts of rigorous analysis techniques do help to find those, and there's many interesting examples where they find them. I know when that thing happened with Boeing, a lot of formal verification people were actually called in to help find where the problems were.
Right. You mentioned that it's a good example of where our research areas actually overlap. In that I look at a lot at organisational cultures, the extent to which culture or internal processes can lead to these kinds of failings. So the extent to which a lack of training, perhaps for individuals within the organisation, or perhaps miscommunication or lack of communication about certain training requirements and so on. And the interaction of these more technical and the more socio-technical issues, if you like, can produce these.
Absolutely, and that's where tools like this really help. When they give you this sort of diagram, when they give you the logical formula, you can actually say, this is what this sentence means. Is that what you wanted to know? And if the answer is no, then they need to go back and fix the requirements. And like when we were doing that use case with Collins Aerospace, they gave us a quote at the end that said, they forced you to think about what the requirements actually meant, which for a giant aerospace company shocked me to the core of my being. But it did emphasize that these techniques, although, they're not as widely used as maybe they should be, but they are very, very useful in critical domains.
Yeah. Absolutely. Any final questions for Marie? Well, thank you again. We'll move on.